All right, so here we're going to address a notion and really define a notion of what we mean by the average value of a function on an interval. So consider a function and consider that function along some interval AB. Now you can see from sort of looking at the picture that maybe the function hits a minimum value, maybe of about that height along AB. You can see that the function between A and B hits a maximum value of about that height. It would be reasonable that the average would be between those two values. But then the question is, how are we going to construct the average value? And we're going to do it using our knowledge of the integral, using our knowledge of how that relates to area under the curve. Because here's the deal. In a way, to get an idea of the values of this function on this interval, you could look at the area under the curve. The area under the curve would give you an assessment of the values of the function. And then, what is the average? The average is going to be a single number which captures what the function does in effect. So what we're going to look for over here is, what is the average value? We want a single number. A single number, the average value, is going to be that number to where if you had a function that was flat at that value, the area under this function would be the same as the area under the original. So, in other words, whatever the integral of the original function is, this is the area under that curve. Our average value is going to be how high we'd have to build a constant function which would have the same amount of area under it. Because think about it, if we built this average value too low, we would not have enough area to have the same area as what's under our function. If we built this average value function too high, well then we'd have more area than we have under our function. We have to sort of get this average value just right. But the average value is just right when the box here on the right has the same area as what's under the function. But then what is the area of this box? Like any box, it's just base times height. What's the base? The base is b minus a. That's the distance along the x-axis. What's the height? The height is the average value. But now, the whole purpose of this activity and sort of discussion and dialogue was to nail down what the average value is. Well, you see, if the average value multiplied by b minus a is the integral, well then divide both sides by b minus a, and we can say that the average value of our function is just whatever the area under the curve is divided by b minus a. And the long story short is, this is going to tell you how high you'd have to build a box so that that box would have the same area as your original function. Because when you know how high to build the box, now you have a single value which captures the same amount of area between A and B as our function, which was undulating up and down. And what is an average again? It's a single number that captures some effect related to the data. That sort of is some number that sort of summatively looks at the numbers and says, okay, this is, if you only needed one number to capture what's going on with that function, here's what you'd need. The average on a quiz is this. Why? Because it's one number that sort of gives an idea of what the total values were. Well, the total values of this function are going up and down, but we can nail down a single number, which would be the area under the original divided by the width. That would tell you how tall to build a rectangle that would capture the same amount of area under it as under the function. And that is precisely what our average value is. Okay, so if the average value is this, what can you sort of do with this idea? Let's go through an example. Let's find the average value for this function. We've got the function f of x equals x squared plus 7. This is some function. In fact, if you want to think about what this function is, it's a parabola shifted up 7 units. And certainly there's some amount of area under the function. And well, the function values are going to be between a certain number and another number. I mean, hell, they're going to be between what? Plug in 1, they're going to be between 8. Plug in 3, 16. You know the function values are going to be between 8 and 16. The question is, what's the average value? What would be the value between 8 and 16 that if you built a rectangle perfectly flat, constant across, you'd have the same amount of area under it as you have under this function? Well, to do that, we'll cook up what we did previously, which was our average value formula. So we'll first compute the area from 1 to 3 of x squared plus 7. And then we'll divide by 3 minus 1. This is the average value. This is how we define the average value to be. The average value, the height of the rectangle, such that the area under the rectangle equals the area under the original function. The average value boiled down to the integral divided by the width of the interval. So we compute the area under the curve. This is going to be what? X cubed over 3 plus 7x. But we still have to evaluate between 1 and 3. And this is going to be all over 3 minus 1. So all over 2, I suppose. To do the area under the curve, you first have to find the antiderivative function, which we have. But then you have to plug in 3. So we'll get 3 cubed over 3 minus 7 times 3. And then you subtract the antiderivative function plugging in the lower bound, which is 1 in this case. So we'll have 1/3 plus 7 times 1. And, well, let's run the numbers here. 3 cubed is 27, divided by 3 is 9. Minus 7 times 3 is minus 21. So 9 minus 21 minus 12. And then this additional number over here, then we got 1/3, and 7 1/3. So that's minus 7 1/3 minus 22/3, and this is all going to be over 2. So if we're subtracting 12 and 22/3, that's minus 36/3 minus 22/3, all told minus 58/3. That's divided by 2, so if minus 58/3 is being divided by 2, oh crap. I'm realizing I made an error here with a minus sign. Son of a gun. Well, so be it. Let's correct ourselves to make sure that we get it right. I put a minus sign here on the minus 7 times 3. I don't know why I did that, because the antiderivative function had a plus sign. So 9 plus 21 gives you a positive 30. And we have a positive 30 minus 22/3. Positive 30 minus 22/3, that's going to be 90/3 minus 22/3. That's going to be 68/3 divided by 2, but half of 68/3 is 34/3. And we've got it. Okay, so what's the long story short whenever we're doing the average value in this particular example? Well, like the average value always is, it is the number that if you built a rectangle, so in this case, go up 34/3 and build yourself a rectangle. The rectangle that's up 34/3 is going to have exactly as much area under it as the original function had under it. How do we know this? Well, because the average value times the width would be equal to the area under the curve in order that the average value be built at the proper height. So when we take the integral divided by the width of the interval, we get precisely the average value, precisely the height of the rectangle we need. And in this case, it happens to be 34/3. By the way, how I knew that I was making a mistake before I actually ran through the computation and just circled it and stopped the video, when I was running the numbers here, I was getting something negative. And whenever I looked at my original function was living all north of the x-axis. My original function had a positive area, so I knew the average value, well, specifically was between 8 and 6, but it definitely had to be positive. So whenever I had something negative here, I knew the average value couldn't be negative because it would be impossible for a negative height to capture the average of a function that lied between 8 and 16, a function that lied above the x-axis. But the long story short, when you calculate an average value, you're getting the height of a rectangle whose area under it would equal the area under the function, and you can always find the average value by first computing the area under the function and then dividing by the width of the interval.